Yes. So yeah, I'm Markku. I currently split time between my home country of Finland. I'm a professor at this university, and Taiwan. So I'm involved with Chelpis Quantum Corp in Taipei. Yeah, a little bit of a history. So actually 1 week ago, in Helsinki, we had a 30-year celebration of SSH. So Tatu Ilonen, I believe, released the first version, public version in 95. At that time, I became involved shortly after that. So I still remember the day when you could telnet to gary7.nsa.gov and get a username prompt and all of that. So now they are happily using our software. So I was also the editor of the specification, and I'm an actual cryptographer. So sounds funny saying that, but it's so yeah, I was editing we basically designed the protocol. So OpenSSH came later, but they just use our protocol. Now the outline of this talk is I'm going to be talking about some stuff no one knows what Adam's breach is, so I need to explain what Adam's breach is and why you guys, hardware hackers, will be running into it a lot in the near future, I believe. And also Calyptra 2, so Adam's breach is a part of Calyptra 2. Then a couple of little attacks here. So there was also in previous talk, there was stuff about bypassing signature verify for secure boot. There's a little strategy I have for that with this particular root of trust secure boot mechanism. And then some side channel stuff in a very basic leakage assessment. So this thing is, by the way, not in silicon yet. This is still being taped out in very rapidly by some companies. But we can do simulation, and we can see that it actually sort of leaks the secret keys in this sort of silicon testing. Well, you at least leaks information about the secret keys. That's a little different. Direct exploitation might be tricky. And if I have some time, I put some code online 2 days ago, which basically wraps this entire Adam's breach into a nice single executable, which is able to produce these traces, and you can try it out. It's able to do a full dump of 40,000 cycle execution in 1 minute. So I was able to do 10,000 traces, so I can plot nice with a big computer. I can plot nice trace like TVLA plots and things. So now, what is Calyptra? So Calyptra is this project under Chips Alliance. It's mostly being developed by Microsoft. Looking at the GitHub commits, AMD seems to be really interested in, and then there's NVIDIA and Google also involved in this project. Google is, of course, for example, also involved in OpenTitan, which is another root of trust secure boot mechanism that they are using, and they have Titan and they have other things. So what Calyptra does is measured boot. I believe the first version, which doesn't have this post-quantum stuff, was already put into production in some server hardware that some of these subset of these companies have. Now, Adam's breach is the code name specifically for the post-quantum crypto hardware accelerator for Calyptra. So this is the first version that just was, I believe, in March. They froze the RTL, and it went into some kind of third-party security evaluation, and they announced that version 1.0 is final in May 1st. I'm using that version, so it's like about a month old. So obviously not in silicon yet, then there's been some patches on that. So it supports only a single algorithm and a single parameter set of that algorithm. So MLDSA is basically what's going to be replacing elliptic curve signatures and RSA signatures in these sort of secure boot things in many places. So in my previous life, before coming to Tampere, I was a principal engineer at PQC, Shield, where I actually also did a hardware root of trust. So many of these silicon companies actually we've been licensing those out, and we know that they are popping up in near future in many places. So yeah, the Calyptra people have been putting out things like this, which seems to imply that so these technical adversary council companies committed to deliver products with Calyptra in 2026. So the underlying RTL and firmware providing secure boot, like even before the main CPU wakes up. So this is before your trusted execution environment and all of that, is this thing. And it's open source and you can download it from there. So yeah, there's some block diagrams here. So there's a typical SoC architecture. You have your AXI bus and you have a Calyptra box in there. Then there's some other boxes, rest of SoC. Inside the Calyptra, there's a self-contained green box here which says Adams Bridge, and then there's like Adams Bridge SRAM for some reason outside the box. A little strange, but yeah, so this is what I'm actually focusing on. Now, why would all of these companies be needing a root of trust unit? So of course there's AMD, for example. Even a processor itself has firmware called microcode. Microcode tells the processor what each instruction actually does in a sort of Intel-like architecture. So, for example, this was exploited earlier this year. I think this was called entry sign. It was found by Google. Their POC was pretty funny. It was they were able to forge signatures for a microcode update on AMD Zen microarchitecture 12345, which is almost the latest one. And this POC was funny because it modified the RT-RAND instruction, which creates cryptographic random numbers to always return 4. So that's that's also a random number, but you wouldn't always expect to like continuously just get 4s. And this is like a classic sort of example of a sort of a very, very problematic area. If you're modifying actually what the microprocessor instructions themselves do. And it's very difficult to detect, so you can imagine a supply chain attack where I hack your processor in a way that your secret keys are no longer secret to me if I activate something. There's Trojans you can do in microcode, there's anything. So why this happened to AMD is that they had RSA signatures, and of course, what you do first is compute a hash of what you're signing. They were not using a hash function. They were using a MAC. They were using CBC MAC. Now, there's a difference between a hash function and a MAC, is that the MAC has a secret key. Of course, that secret key happened to be the one you can find in FIPS examples in the datasheet. So that was very easy. So they did the math and were able to create these forgeries without breaking RSA or anything. So this has nothing to do with post-quantum itself. But yeah, so, and same thing with GPUs. There's massive amount of firmware in every NVIDIA chip. With FPGAs, I'm not talking about that they would put this hardware into the FPGA logic fabric, but they use this hardware to basically verify that bit stream. The thing, binary blob that defines what an FPGA does is also signed. So this is in actual like static silicon. That's what Adams Bridge is doing there. It's the core signature verification function in there. So why is there such a rush with dilithium? Well, it's the law here in the United States. So Joe Biden put out some executive orders, and they are still in force, and more specifically for NSS, which is the sort of crypto used for defense and intelligence community. They have a fairly hard transition deadline. So now it's saying from the beginning of 2027 in new products, you should have this CNSA 2.0. So CNSA 2.0 no longer even mentions elliptic curves or RSA. So this is the signature function that you actually have to use. It's depreciated. And if you know anything about hardware timelines, you know, it's one thing to have a design, then you do a tape out, you send it out for fabbing, then it comes back, then you put it on a PCB somewhere, and only at that point, sometimes people start writing like actual drivers for it. So it takes a long time for this cycle to complete. So in order to have these products ready in 2027, we, for example, in my previous company, were already selling this stuff in 2022. So that's the situation. Yeah. So this is like from the policy document approved up to top secret. That's where you gotta use. No RSA here, nothing like that. You can the CNNS website. It has a funny DoD cert, but you can actually go and download this policy if you accept that cert. Now, and another thing that NIST is saying, they actually have the word disallowed for RSA in 10 years. So of course you can carry RSA around, it just doesn't count as crypto anymore within 10 years. And of course you cannot get like FIPS certified or anything. So that's why this changes stuff a lot. By the way, I should mention that the sort of compute you need for dilithium is completely different from RSA and elliptic curve. So RSA and elliptic curve were big integer stuff, number theoretic things. Here we are doing a specific type of ring arithmetic, which using number theoretic transforms. That old hardware, you can't use that to accelerate post-quantum crypto or the main algorithms. So the status is that you can go to this GitHub repo and get it from there. Is something like 47,000 lines of system Verilog, nothing else. It's like it's all hardware. There's the module itself is like that. Yeah, like I mentioned, I'm using the release. It just came out after this external evaluation in what I'm talking about. It only supports this one parameter set 87, which is category 5. That's the highest security level. That's the one that they approve for top secret in this sort of a defense setting. The module is really like a fire and forget in a way. So it has four functions only. So it can create a key, it can sign, it can verify, or it can do this combo move of key generation and signing, because it so happens that in dilithium key generation is much faster than signing. So you can just store a seed that you sort of expand into this secret key and you do a sign like that. Yeah, so they seem to have like moved on very rapidly after this. So like during last week, they've started adding MLChem commit. So MLChem or Kyber is the key establishment algorithm. So this is what will replace basically your Diffie-Hellman key handshake. Has already actually replaced about 40% of those, or there's a hybrid method that Google has universally adopted, and Cloudflare or something like that. Cloudflare radar says that 40% of TLS handshakes are now actually Kyber. So this is happening pretty rapidly because of these deadlines. Anyway, so for us hardware people, this affects things. So one of my affiliations, I'm wearing a RISC-V T-shirt. I'm the chair of the post-quantum task group at RISC-V. So this means that the ISA itself will have to change. We might need new instructions. We actually need a Ketchuk instruction now, because all of this is based on SHA-3 and so forth. So this is because we adopt a quantitative approach. We do micro benchmarks, and we see what instructions are actually useful in the RISC-V world. So yeah, we have to do stuff for post-quantum as well. Anyway, so architecturally, it's a funny one. It's because it's all just like bolted down. It's all hardware. There's like a separate little modules for all the functions that you can find in the standard. So there's like a function called use hint. They just turned that into a hardware module with wires going in and wires coming out. This is actually a rather unusual way of doing hardware design, but that's what they ended up with. And it's really, really big. So the specification currently gives out an area at 5 nanometer node and 600 megahertz. By the way, these so root of trust units are typically clocked a little bit under like 500 megahertz is normal, because it's not dependent on the main CPU. There's a limited communication between a root of trust unit and the main CPU. But the root of trust unit is the boss. So okay. Anyway, they're clocked a little bit down there. It's mostly standard cell, so there's a lot of logic in there, a little bit of RAM. And, well, it's a little tricky going to gate equivalence from an area at this node, but I guess it's about 3 million gate equivalents. That's enormous. I did FPGA synthesis on it on ultra scale, and that kind of matches with this sort of a guess of the gate equivalent area. So this is the size of 30 microcontrollers, like Cortex M3. It's really, really big. And a Cortex M3 would be able to actually compute dilithium, so it's a little odd. Yeah, so a Cortex M3 is about 100,000 gates. And other hardware modules actually, which are able to do all kinds of stuff in addition to just this particular function are about like 1/10 of this size. So that's a comment on this particular thing. But it's pretty fast. So with the repo I gave you, you can do cycle accurate. You can just run the entire circuit. You can do a signature in a minute, and you can do verification under a minute, and you can see all of the signals, everything that are happening in there. So in case you try to actually glitch, this is a little different, glitching actual hard-coded hardware, but you can find the signals going on in there. What we don't know yet is because place and route can do random things, so we don't know where these signals will end up with, but this is as good as we can currently do. Anyway, so in order to do a signing, if you're a host CPU, you just write the key at one address, you write some random numbers in another address to randomize it. Your message hash in one point into registers, and then you say go you just write into a single register, it'll start crunching, and after a while it's like microwave over and go bing, you have your signature ready here, no interaction whatsoever. So that's the way this thing is built. One thing to note is that with any dilithium implementation, the signing process has these rounds. In each round has about 25% probability of success. So by random chance, and these are like independent dice rolls. So you're like rolling a dice until it's like 1 or something like that. That can take any number of times. So it can. So the actual timing of the signing process can be sometimes pretty long. Now coming to the main sort of very basic things. So I'm a practitioner. I have some more like fancy side channel emanation stuff, but obviously the most obvious attack is just faulting verification. Can you easily bypass this verification function? Because that's a yes or no answer. Is your signature valid or not? If you can, it's 1 bit. So if that's why we typically have quite a bit of redundancy in this verification. And sure enough, Adam's bridge also has this. So they have this countermeasure where instead of returning that one Boolean flag, is my signature yes or no correct? It actually, you read out 64 bytes from a certain register. And basically that 64 bytes that you read from there, you need to compare to the beginning of the dilithium signature. So if these 64 bytes you get, it's a specific value match with the 64 bytes from the signature, then you judge that to be a valid signature. So that's the countermeasure, and this is all that the hardware spec said. So you can actually find it. It's all open, and it's actually pretty wild because you can sort of see them live coding the thing because every day there's commits. OpenTitan doesn't work like that. They have like a secret branch and they just commit from there. But these guys are like doing bugs and So it's fun to track. Now, just to explain how that works is that this is from FIPS 204, the dilithium standard, the MLDSA standard. It has a function algorithm 8. This is the pseudocode for verification. The beginning of the signature is this C tilde value, and in the signature verification process, by the way, you can see that the pseudocode is crazy more complicated than, let's say, RSA verification function, which is like one equation, one line. Here we have 13 lines of pseudocode just for verification. And on some of the lines, it's actually doing multiple things. Now, and it's calling subroutines like this, like the decode function. Now, the C tilde is the first 64 bytes of the signature, and it recomputes this C tilde prime here at line 12. And then in the official pseudocode, there's actually the same kind of check here as well. So that's actually a sort of a pretty clever way of doing it because the pseudocode also has this verification function. But then we observed that there's these other return statements here, like what happens if the signature has some malformed stuff? What is the return value then? Actually, the hardware specification didn't say this. Like, this is an early abort. So this is even before the C tilde prime is even computed. So, I mean, and then there's this other sort of a check on this, line 30, which is actually a bounce check on this Z signature vector. which, yeah. So one way of finding out is that, I have the hardware source code. I can simulate the whole thing easily. So yeah, it just returns 64 zeros. Now, there's nothing preventing me from just like making up a signature that has 64 zeros in the beginning. So yeah, so that's one way of kind of creating this really stupid forged signature. So the comparison will match. The firmware will see, oh, zeros is zeros. Your signature is valid. And the funny thing is that this kind of signature is valid for any message, any public key. Because it's based on this malformed signature thing where you bypass the thing. Now, yeah, I did the thing. I sent an email to Calyptra security disclosure thing. They were actually pretty rapid in their response. So a couple of weeks back, it says that, oh yeah, we should probably document this thing. And that they did some analysis and they think that this all zeros is the only other case that a failed signature can have. That's their opinion. I don't know. And then they say that, oh yeah, we are also resetting this every time, so it should be definitely zero. So it's not getting the previous value from like previous signature verification or anything like that. I'm not okay. But what this definitely means is that the driver needs to do some additional checks and stuff on the signature before even like pushing it to the Adams bridge thing. So it's not like a fire and forget thing anymore. So it's like a cooperation between the driver and the self-contained unit actually doing the stuff. But, it like pushes a little bit of the responsibility for the driver. And it also means that part of the security now lies on the driver. So I can like attack the glitching. I can attack these additional checks that the CPU is doing. So it's like two-part game now. Indeed, I did find then this comment. So from March, it's not in the main branch of the driver firmware. It's in some branch of 2.0 branch. It was put there in March. So actually before. So perhaps this was after the RTL freeze. Perhaps they found this during their third-party evaluation. It's kind of obvious bug. So yeah, fair enough. They had a fix. So I looked at the source code. So if my reading of Rust is correct, it's in line 455. They're doing a couple of funny things here. It's just a plain comparison. There's no redundancy in here. So you can just glitch this. And this is a CPU thing. So to be fair, the CPU the little microcontroller they have in Calyptra is this Veer core, which has like protected PC and such, but actually glitching something where you compare because I can flip any bit in those 64 bytes to be non-zero, and then this check will say that, oh yeah, it's not all zeros, and you can proceed to the next stage. This looks like a very easy glitching target from that viewpoint. Another thing is here that it's no longer a yes or no answer. It actually has this special error code. So it's you can have a valid signature and not a valid signature, or you can have a bad signature. So from a security engineering viewpoint, this is a bad practice because you are basically offering what we call an oracle to the caller, which helps us to find this glitch position. It tells about the internal state of the target and so forth. So anyway, this is what it currently looks like. So yeah, it looks unprotected. We can glitch this all zero comparison probably. And then we have an oracle here. So anyway, so the way to attack this currently would be this combo strategy, that we first create a malicious firmware with a signature block that has the first 64 bytes to zero. We offer that as either as a boot image or as a firmware update to the target. Like, here's your new microcode. Can you put this run this please? And then when it's doing this signature verification, we actually glitch not the Adams bridge unit, but the little microcontroller on the root of trust unit. So that will be my current approach to attacking this. But sorry, I can't demo it yet because it's in some crazy branch that's not even the main branch, and I would, I would be doing their DevOps for them even to make it run. So it's not like possible. And another thing is that this this whole Adams breach is so large that even getting like an FPGA that fits it, we can't use any more the old tools that we used. We have to get like a new $10,000 FPGA that's just like big enough to hold this. No. Okay. Or we can wait for a silicon target, which probably some of you would do, just like, I know how to break this. I'll just wait until they do tape-out next year. And then they can't change it anymore because it's all bolted in hardware and completely impossible to change. This is in zero-stage boot. So it's in ROM. You just, once there's a bug in there, yeah, you cannot get rid of. Everything after that, you can update. Like first stage boot, your trusted execution stuff, whatever, operating system. This is like way below all of that. Okay, we'll keep tracking this. Now, another topic is the leakage stuff. So they make some pretty bold claims about side channel security. I've been like working on post-quantum for some 10 years now, and I know that this is not a super mature field. So we've known for a long time in the industry how to protect like elliptic curve, arithmetic, and RSA against all kinds of attacks. There's like a fairly well-established ways of doing that in hardware. Most vendors do the same tricks. But in dilithium, not so much. So they are claiming even acoustic security here. A little unusual, but yeah, sure. Now, there was earlier work from Florida Atlantic University, actually, where they attack a specific multiplication step where the secret key component S1 is multiplied with one of the inputs. So this was before the Adams breach group even added like proper countermeasures. So last October, this was the situation where there was no countermeasures at all against this, but somehow they were like claiming it. I don't know. So at that time, you could do 10,000 traces to recover the secret keys using this smaller FPGA target that even I have. There was a paper came out in IEEE host conference. I think it was held here in Santa Clara like a month ago. Reza and Merv, the authors from Florida, actually ran a whole tutorial about like how to recover these secret keys from there. Fair enough. They've now, since last October, they've actually added these countermeasures. So now we are currently tracking like, are the countermeasures any good? So this is the setup they have. This is a really traditional classroom side channel setup. You have a CW305, you have a picoscope, you get traces, you do a CPA, the sort of a correlation power attack, and you extract the secret key with 10,000. So this is a success ranking. 10,000 sharply, they converge on the correct secret keys. Now, looking at some of the slides from the authors of this thing, what was their approach to developing these countermeasures? Apparently, they had this sort of a reactive approach. Come on, they're Microsoft. So it's like if someone breaks something, we'll fix it. That sort of thing, rather than, a cryptographer approach would be let's do a really careful analysis of what are the secrets and develop countermeasures and then proceed to implementation. So yeah, so this seems to be the thing that review existing literature. This is actually a slide from their slide deck, from last October. Review existing literature, list existing essays. But, there's no this is the first open source implementation. There's no literature on attacks, only about protection. We've done research on this, but, there's no commercial implementations or open source implementations to attack. Now, there's like, okay, here's a screenshot from one of the better papers about doing countermeasures, and you can see that there's many more red things. So this red box is signify sensitive variables in the flow, something that you can use to create forged signatures or extract the secret keys. And they should have like countermeasures in all of these red boxes, but they don't. And of course, the main technique that we use to protect against side channel attacks is masking. So the strategy of masking is that you take every sensitive variable, you split it in random fashion into multiple variables, and then you do arithmetic magically on those shares. So you can then do a proof that even if you have a probe there, getting full information of one of the shares, you actually don't learn the full secret because of the way it's split randomly. So that's masking. So Adam's breach claims to have masking, but this kind of requires that your secret key is in multiple shares. It's not in multiple shares. So their masking is not masking as we would understand in cryptology. So yeah, so this is why I was just saying, in actual masking, we split all secret variables into shares. And one thing, sort of a philosophical thing to note about PQC algorithms is that because the pseudocode you saw, even for the verification, has so many steps, is that you actually have to handcraft and prove so many different gadgets for each one of those steps that even touches some of the secret variables. That is a pretty daunting task. So a sort of an implementation that does this in firmware, like in a sort of a more traditional architecture where you have some kind of firmware controlling some hardware. The firmware itself is thousands of code lines long, just because the countermeasures are so complicated. Anyway, yeah, they didn't do any of that because they are patching an existing implementation. So RSA, which is or elliptic curve, RSA is just one modular experimentation. Elliptic curve is a scalar multiplication. These are just like single operation. You do one set of countermeasures is enough. Here you need a lot more work and a lot of more expertise actually to do all of this stuff. So there's some teams actually that have done that. No. Moving on. So what they are masking here seems to be this pointwise multiplication step and inverse entity step. So precisely the things that were attacked. And it's not really masking because they are splitting the secrets into shares just before this operation and then apparently like collapsing it back again. So in masking, we actually keep the secrets in these shares all the time. Yeah, so it's not masking, it's something else. Now, yeah, secret keys are not masked the way we understand it. And remember that there's this feature where you do key generation basically for every signature. This is what we expect to happen. So that part is not, there's no countermeasures there at all. And well, they say that, oh yeah, you don't have to do that with correlation power analysis. But who said that correlation power analysis is the only thing such an attacker can do? That's like the most elementary attack you can have. And of course you can't prove anything because you are not doing anything. So this is like not in sync with the, what a professor would have hoped them to do. Now, anyway, so coming to my simulations real quick. So a little bit of DPA, the differential power analysis, and fundamentals is what causes this leakage is toggling. So if you have a logic change 0 to 1, 1 to 0, there's some switching power, and there's also static power, which is, but generally speaking, if pitch don't change, then it's not leaking. So that static power we don't care about as much. And the same sort of effect also happens in electromagnetic spectrum. Zeros going to ones and ones going to zeros, then we get leakage. And in a more complicated design, anything can leak. So it can be your registers, it can be your memory rise and read, or it can be any kind of internal holding stage in your design. So one should actually understand the entire RTL of some kind of target in order to say anything about this. So anything touching your secret and loading it and pushing it forward in hardware, we have these holding registers. Secret goes there. It actually depends on whatever was the value in that register before is the distance between those values. These two values, that's what you get. Now, looking at the Adams breach, yeah, there's no processor, but there's a sort of a finite state machine in there, obviously. It's a complicated algorithm. You have to implement it somehow. So they invented their own like little sort of a processor in there. This is pretty fast to simulate. I've told you a couple of times already. We can, Verilator is able to run about 3,200 cycles per second. It's a big design, so that's actually pretty impressive. The way Verilator does it is to compile the whole thing, optimize it, push it into a C compiler and get a binary out. And with the full VCD dump, it's about 600 cycles per second. So there's this tool available. So VCD dump allows us to simulate the this sort of a toggling of the design on an abstract level without actually having an FPGA. So this is what I used when I was designing these sort of secure chips myself. And one nice thing about that is that these simulated signals are very, very clean. You need less of those rather than going through the FPGA synthesis. And another thing is that because we have all of the data, we can exactly pinpoint where the leakage comes from. So we know down to a signal where each leakage is done. So this is like a perfect tool for that. Now, okay, using that repo, there's even a nice little plotting feature. You can get sort of a toggle traces like this. And then I have some stuff about how do we actually do TVLA? So leakage assessment. TVLA is the standard way of testing, if your hardware AES module, for example, is leaking. So even on contracting, like semiconductor contracting, we might get a requirement that, oh yeah, you need to pass TVLA for 1 million traces, and then we'll buy your thing. And by the way, I've done that sort of contracting. So for PQC algorithms, it's a little funny. So this is the basic t-test that we use, is that the dilithium secret key is not completely secret. So there's actually 6 variables in the secret key. There's raw, which is also in public key, so that's not secret. There's K, which is used in some kind of deterministic mode. There's TR, which is a hash of the public key, but somehow it's contained in the secret key. And then we have the 2 actual sort of secret variables, S1 and S2. So how do we test this? Because the traditional way of doing TVLA is that you compare traces from a fixed key to a bunch of random keys. And if you can statistically distinguish these 2 sets, then you can charge that, oh yeah, it's leaking. But because we are obviously not protecting something like a public key, which is also in the secret key, then this would create lots of false positives. But there's a little trick to this. So this is the key generation thing. We just modify the key generation a little bit so that everything is randomized except S1 and S2. So this helps. So if we get this sort of a statistical differentiation, distinguishing, then this allows us to attribute that statistical leakage directly to S1 or S2, the actual secret keys. So this is one way of doing TVLA on dilithium. Okay, so I did that, and it leaks like crazy. No one is surprised. So for us, typically 4.5 is the critical value. Here's 150. Of course, yeah, but that was completely expected. So this is 11,000 traces. Zooming into the beginning. So this is right there in the beginning, and then there's some wild other leakage after that. One interesting thing to do is because the TVLA math is based on this Welsh t-test, which is based on the you have set A and set B, and you have a standard deviation and average of these, which is what you actually compute, is looking at the standard deviation. So the standard deviation plot between the fixed set and the random set are really easily readable. And because we are doing pre-silicon, we can actually get the single names. So for example, this is called SK decode. So that's doing a secret key decode. It's reading the secret key, which is in plain text, and putting it into some entity register. So of course that will leak because it's plain text. The secret key is plain text. And then there seems to be some bugs perhaps in the countermeasures. Now, what we can say is that, yeah, it leaks because it's not protected. But it's actually maybe in practice be saved by being really fast, because it's super, super fast. It's 10 times faster than some other hardware implementations, which means that it's moving a lot of bits in parallel. So if you are looking at the power traces, you are just learning the grand sum of everything happening in there. So that might be actually a saving grace in this situation. But yeah, we could have not sold this. It was in our contract, and you need to pass the TVLA and all of that. So yeah, Microsoft, I don't know. So this is my summary now. So because of this regulation, hardware people are in almost panic mode getting this stuff out. And in 1 or 2 years, you will probably be bypassing this kind of hardware a lot. And my trick for bypassing the signature verification actually involved a little bit of cryptanalysis, actually understanding how does the verification works. So it's worth studying. standards now, and at least at high level, we are not breaking the learning with errors problem here. But we kind of have to understand how stuff works. One thing to note is that there's been I've been working on this for 10 years, so there's been actually quite impressive and not less impressive research work on building these countermeasures. So one should probably use it. And I would recommend a systematic approach, doing this sort of a sensitivity analysis, figuring out exactly which variables are secret and which are not, because the secret key has public variables, and so forth, and then doing masking. And as noted, this is available in this public repo here. Yeah. So.
Test. Thank you for your talk. We have time for some questions. I guess if I can start. So the huge space of the chip, does that include like some microcontroller verifying the 64-byte, or is that like entirely left up to the firmware calling into the hardware module?
Yeah, it's back on. So this is Adam's bridge alone. So Adam's bridge includes everything it needs. So for example, if you have it, you have multiple copies of SHA-3 because it uses hash function, so it has hash function built into it. For us hardware designers, SHA-3 is really, really big. It's like 30,000 gates, so you wouldn't do it wastefully. But that's how they architected it. It doesn't have a microcontroller, so it's a dumb hardware module. Just is able to do signature. It doesn't. If you have bus access, you can write to the registers. It waits for the go signal. It does a thing, and then it just sets some kind of status register saying that it's done, or sends an interrupt to the host. So it's supposed to be this fire and forget type of thing. So the really big hardware size. My guess is that perhaps they were writing it like software. So these people didn't have like the circuit in their head. So that's why they were like unrolling loops into hardware. Fair enough, that makes it fast. But on the other hand, it's kind of too fast. You see, it's doing verification in 17,000 cycles, but a signature verification in a boot process, you can do at the same time in parallel when you are doing the hashing of the image. You don't have to wait until end because you can store the hash in the beginning of your boot image and start doing verification, and at the end compare if the actual image has that hash. So this is a parallel process. So and so while you are doing hashing of your gigabyte image, even a much slower implementation would have already verified the signature. So it's not in the critical path. So for this purpose, this is way too fast. And the signatures for attestation, they don't need to be in microseconds. I mean, come on. It's attestation. You use that once in a year.
All right, thank you.
Right.
So you told us that they're doing the masking insufficiently. Presumably you've told them, meaning the Adams Bridge designers. What has their response been?
I have not directly told them. The thing is that it's quite obvious that you have to think of masking first, because all data is in multiple copies. You have to build your hardware architecture for that. So it's difficult to batch something like that without a complete rewrite. So this is really the lessons learned on that. I did communicate the fault attack, and there was a response from that.
Right, that's sort of why I'm asking. You've already reported an issue, but this is a much bigger and more fundamental issue. And I get that you're saying, okay, they have to rewrite it, and all the hardware they're taping out needs to be junked and restarted.
Yeah. So the thing is that I'm not like extracting secret keys. So in some. You might be able to pass even common criteria at some level using this kind of implementation. Common criteria at Ava1.5 has high requirements, but it kind of expects that you are able to extract the full secret key. I have not been able to do that yet, but I can extract information about the secret key. A lot of information, but not the full thing. So perhaps, at that point I would certainly And there's so many moving parts because it doesn't, it's just simulation.
All right. Maybe one very quick question.
So is your pre-silicon level the TVL test based on the RTL level?
So very, very later translate system Verilog into C. So and the signals are in the RTL. So it doesn't do a netlist. So I have other tools for netlist that might be actually better. So, but this is a faster way of simulating stuff.
There's a result unprotected implementation. So can you try the protected?
So this is the mass protected version that they have, the big one. So there's a size difference of like twofold between the protected and unprotected, and this is the big one. And I believe I was doing everything correctly. So I was feeding it randomness, and for every trace and so forth. So
after logic synthesis and place and routing, has a similar result.
So this is so it takes the system Verilog directly and translates that. So it doesn't do a netlist stage even. So So you can a lot of people do pre-silicon like that. You use Yosus or some other synthesis tool, and you get netlist, and from there you can get like register toggles and things. So that's a little bit slower, but it's as easy as to do. So, but I can run like a microcontroller in almost real time using something like that.
Right. I'm sure Markku will be around for more questions later at the conference. Let's thank the speaker again.